KDP crystal, and a lot of glow even at that age of maybe 70s or so years of this. So now of Raman spectroscopy, the Raman fine details about the matter, including the material science, but also in there may be impurities also, and molecules, etc. So that is the basic principle of this. So actually, first, in addition to the electronic levels, these are different varieties actually. This is a symmetrical stretch, this is a symmetrical stretch, and this is, that means if you know such a small molecule, okay, functional natures, they always move from their average position, and they have a maybe at a stretch in the extra energy to the incident radiation and their wavelength, some energy in Stokes line. This one is 1 by lambda scattered. So we can define the Raman incident light is known as Raman scattering or Raman effect spectrum for us, and with that we can groups, and when they are stretched or when they may have some strain, have grown this silicon germanium relax a little bit. That means this lattice may shift away from the strain in the layers effect or Raman spectrum. Okay, next is because it is very sensitive to the about the Raman. Just I wanted to introduce what is Raman effect and what it can do with a simple example of this medical diagnosis in the quantum technologies. Basically, here you see it is not a it took a momentum of very safe and unhacked way of sending the information. Shor develops a Shor's algorithm for factorizing large numbers using quantum computing algorithm, and successfully it has shown. And then later in 20s to the so far there is a lot. So this is about the quantum bits, and actually you see first we should know these are which on or off. Okay, so that is the what these are actually. This is the unit, this cat 0 and cat 1, and in the qubit it is not like that. Simultaneously it can, but it is not possible here with the classical computer, either 0 or 1 at once. Till it fell down, it may be head and tail, both will be there. What measurement will come, we have to wait. So in that way, once we did the measurement, it is now superposition will be lost. But before that, you can do lot of proportion. Actually, how it came actually, suppose it actually same equation. What does it mean? Actually, suppose Q0 and Q1 are the solutions of that Schrodinger equation. So these are, so 0 cat, we call this as a cat, and this is a 1 cat, like that, and alpha into 0 cat plus beta into 0 cat. These are the bracket notation, the famous bracket notation. It tells the state, it tells the state of a quantum bit. Beta, these are the probability amplitudes. So what should be the total probability? Can anybody tell? Suppose the finding of your beloved principal in the total probability 1, it cannot be less than 1 or more than 1. So therefore the amplitude, the square, the sum of the square of the amplitude will always be 1. Okay, so alpha and beta are in such a way that the sum of the squares of these probability amplitudes must be 1. Okay, it cannot be deviate from 1. So that is the thing. Now we can define a qubit. A qubit is a two-level quantum system that can exist in a superposition of states. This one, and a qubit is how to implement this practically. So it is implemented by encoding information into the two quantum states of a physical system, such as the spin of an electron or the energy levels of an ion, that is ground state or excited state, or the polarization of a photon, horizontal versus vertical or left versus right, circular. So we are actually, these are the qubits or that carry the information. It is a unit of information. But why we are actually encoding our information on a qubit? Because with the qubit you can do enormous calculations. For example, if you have a n qubits, you can have 2 to the power of n ways of calculations simultaneously. Here you can do only one after the another, but here if you have a n n qubits, you can have equations of 2 to the power of n, and you can simultaneously calculate it by all these ways. So at the end you can get a correct result quickly. So it is leading in exponential way of exponential speed. That is one property. And then this is called parallelism. That is 2 to the power of n ways, means that is parallelly we are able to calculate this. If there are n qubits, you have a 2 to the power of n ways. Okay. So that is how you can have a multiple ways of calculations. And so what is actually superposition? Can we really see? Yes, you can at least sense it. Okay, your light around us is nothing but the superposition of different polarized states of the light. It may be horizontal, it may be vertical, it may be diagonal, and so on. It is a mixture of all such polarized waves. Okay, now how you can see that? You see here you are putting one, this is a polarizers. We can have for polarizer, this is called horizontal polarizer. That means here this type of wave only will come out. This vertical will not come out from this, from a unpolarized light. So, and then if you put a vertical polarizer here, no light will come out. No light will come out. When we put a horizontal filter, that will allow only horizontal polarized light. Now if you put a vertical polarizer, nothing will come, because they are orthogonal to each other. But you see, the peculiarity or the surprising thing is that if you put another filter, such a filter, here diagonal filter this is, it is neither horizontal nor vertical. If you put that one, some part will come out, and from this again some part is coming out. You see, is it not something surprising? Because you are putting one extra obstacle in between actually. What you did, something that is also an obstacle. So, but still you are able to observe the light. This is called superposition. We are unable to see in the, okay, in the normal way, but you can see that this superposition. And another very good example I tell you, this is actually, there is a single slit here, and for that single slit, this is the interference distribution, this one, the bigger one. Okay, so along these the paths of the constructive interference, you have a good intensity. Okay, so in a single slit system, you will have a interference pattern. So that is this is one. Now you see here at a yellow point, there is an amplitude here. There is some amplitude. That means intensity is there. But as soon as the second slit is open, this becomes zero. That yellow spot at this one, it becomes zero. What does it mean? As if instantaneously, this happens instantaneously. It won't take any time, not even the speed of light. It is much more than infinity actually. So what that it means, as if that wave is also a particle, isn't it? Dual nature. Wave is also have a particle nature, okay, dual nature of a quantum particles. So it is actually as if the slit is open, immediately it is known to this, and immediately the intensity is redistributing, and where earlier with a single slit we have some intensity, now it becomes zero. So that is also due to superposition. Here I would like to tell one more thing, which I may not again show this thing. You see, there are the constructive paths here. That is due to constructive interference. Actually, while calculations takes place, during these interference paths, the calculation goes exponential with an exponential speed. So that is also an additional advantage because of the interference. Okay, this you keep in your mind. In the due course of time I will tell what is that actually. Okay, so have you understood this interference? Okay, so I will go to the next slide. Okay, quantum entanglement, what it means actually. It is a phenomena where two or more quantum bits are entangled to each other. That means linked to each other. They are having a link in between. So they are correlated to each other. Suppose if I disturb one quantum bit, automatically the other part will be felt its change. So irrespective of the distance, it may be far away, that means it is light years away, maybe on a separate planet also. Immediately it will be felt, whatever the change here, the state of one qubit, entangled qubits only, entangled qubits, automatically it will have the effect on the other qubit. So of this, it is related to this only. Suppose the electron spin is there, spin up and spin down. So spin up is in your laboratory and spin up, the other one is it is expanding, it is spreading throughout the universe. Okay, so therefore immediately it will sense there. So that is called entanglement. So infinite speed, this is absolutely infinite. It is very difficult to believe classically. Bell has proven that it is like that. It is a special only, but they proved later, these people, this invention led to the Nobel Prize in 20. In their laboratories they have proved this. The other laboratory was so far actually. So sometimes we call them as Alice and Bob. Okay, that I will tell you a little later. So now this is called spatial entanglement, and temporal entanglement is another one. In that in that also, that means there is a link, there is a entanglement between the past time and the future time also in this quantum bits. Maybe some applications may come, we can go into the future also, which we were studying in our college times in a non-detailed book, Time Machine, something like that. Now there is no car, but now the flying cars have come. Everything is changing very drastically. Okay, next. Okay, this is actually to describe some of the physics phenomena are related to the entanglement. We take the help of this thing. Actually, Alice is sending, or the information is there. It is she is a sender, and Bob is a receiver. They are basically photon detectors. So if she did a little bit something, even if she tried to measure its quantum bit, automatically Bob will know that she is measuring, and immediately whatever the measurement, the other thing is very corresponding. For example, in a simple way, I tell you, suppose in one in a one basket, one apple is there, one orange is there, for example, 10, isn't it? So it is also something like that, analogy, but a lot of physics is there behind it, but to tell you in a simple way, that is the thing. So sometimes we take the help of this Alice and Bob's experiment to describe some frequently asked questions and answers. For example, does India have a quantum computer? Actually, through these type of questions, a few questions, I would like to give some idea about the National Quantum Mission Program. So it is established on 14th April 2025, and the developer is Quantum Processing Integrated Artificial Intelligence, and a DST supported startup this is, and system is full stack quantum computer, hardware plus software plus AI integration. You see here artificial intelligence, so both are helpful to each other. So that also we have integrated in our this thing, and integrated quantum HPC platforms and AI enriched hybrid computing and scalable thousands and even millions. Okay, so what is it actually, why we have this mission, National Quantum Mission? It is it aims are like this, and quantum, we can import some quantum computers, but eventually we have to develop our own systems. That is one of the thing. And quantum communication networks, we have to establish quantum communication networks, which I will tell you. And then quantum sensing metrology, accurate measurements can do that by quantum sensing. And goal is position India as a global leader in frontier technologies, and the main strategic importance is reduce the reliance on the foreign quantum platform. Quantum computing లో కూడా మనకు కావాలి. సో అంచేత ఏం చేయాలి, ఇప్పటి నుంచి మనం ఇవి యాక్చువల్గా మేము రీసెర్చ్ చేసేటప్పుడు కానీ మేము చదువుకునేటప్పుడు కానీ ఎప్పుడు లేవు. మాస్టర్ చెప్పారు కదా మన ప్రిన్సిపల్ గారు, ఇది మీ చదివాను కాలేజెస్ ఇవన్నీ నేను లెక్చర్స్ రూపంలో మీకు అందచేయడానికి ప్రయత్నిస్తాను. సారీ. సో actually in 2027, by 2027, AP government, maybe with the center, they are going to put this 500, it is already foundation stone was laid down in this month only on 6th February, and the vision is by 2035, Amravati aims to become a globally competitive center for quantum science and technology. So that is the main aim, and these are the layered structure, which I will explain you a little later, why we have to have a layered structure. And this is the present scenario in the world. USA, they have this 127 qubit system, and this China 66 qubit system, and India 25 qubit system. So scaling from 25 to hundreds or thousands is essential for practical advantages, and it needs error correction also, and talent and ecosystem. Yes, IBM, actually we have a tie-up with the Indian government, as a tie-up with the IBM. So they are supposed to train 5 million Indian leaders in artificial intelligence, cyber security and quantum computing by 2030. So even if you have a workshop here or a FDP here, they are supposed to come to you for simulations. We can do that also. Of course, I have had to learn that part. We can we can download the this Quickscript programs that, and we can do here also. But I am now I am giving the theory part, and of course all technical information I am going to give. So is the human brain more powerful than a quantum computer? No. The quantum, our brain contains 100 billion quantum bits, so there is no comparison. What is decoherence and a quantum error? Actually, this quantum information during its travel in a long distance, it will lose its coherence. That means there may be, because of the environmental effects like temperature and other radiations, there will be slight loss of this photon. Actually, photon is one of the carrier of our qubit. So there may be loss. That is called decoherence, and errors may be there because of the your environment. That we have to rectify. So how fast is Google's quantum computer? You see, it is 241 million times than that of the classical computer. In a layman's language, if I work to a classical computer needs 47 years of computation, this quantum computer can do the same work in 6 seconds. You see, such a fastness. 47 years and 6 seconds. There is no comparison. So that type of speed is there. Okay. Let us have a quick look on this artificial intelligence and machine learning and deep learning. So as a definition, AI mimic the human intelligence like reasoning, problem solving, and make decisions. It can take decisions also. How it works? It works on rule-based systems or algorithm to solve the problem. That means rule-based system means we are giving some programs to that. So it will do like 2 plus 4 is equal to 6. We are teaching, we are giving the programs inside. So accordingly it will do. That is one way of operating this. What is the example? So a virtual assistant like a Siri or Alexa that can understand and respond to your question, or a chatbot that can have a conversation. And then machine learning. So actually in this, actually the machine learns. Actually when you give a data sets, huge data sets, the machine will learn from the data set itself, because it can form a fx function. It will learn a function which satisfy the input, and accordingly, suppose square function is there, the input answer will be, suppose input is x, answer is x square. So it will, that is called fx. So that type of thing for a particular data, and it will learn what is the function of those things, and then according to the function it will tell the answer for the new coming data. It will learn from the available data and use that knowledge to the raw data or the incoming data. That is the one. So examples are, it is, that means it is trained itself from the huge database, and to identify patterns or make predictions, etc. For example, a spam filter, so that identifies and blocks the unwanted emails. Some may be spam like that. So from the previous experience, it will tell, no, this is a spam email. It will block it like that. It can take decisions by its own learning. Okay, and then like that, robotic process automation, customer service operations like sales optimization, even knowing the sentiments of a customers as per the data stored in the central AI. What is that actually? Suppose if a person purchases bread, milk, etc., he may also try to purchase a jam bottle, like that. So it can know the sentiments of the customer. He will not ask for a non-veg, a vegetarian person. So that type of things, it will stored in the main central processor, AI information. Accordingly, it will help the customer. It will help the customer. Sir, this is jam is there, bread is there, milk is there. According to his habits, like that it can do. And another one is the deep learning. Deep learning. Here, as I told you, it contains a complex, multi-layered artificial neural network. This is using the advantages of the quantum mechanical principles, and it will handle huge amount of data at its by its decision nodes. It will take huge data and process it. So, and it will categorize into different items like toys, fruits, furniture, and so on. Again, suppose if there are so many fruits and you want to have some particular fruits, for example, it will suppress the common features, like all fruits are round. So that is not a big issue to identify. That cannot be a deciding factor. It will reduce the parameters, and finally it will give a good output, like this one. So output is a limited one. Your result, it is giving the result. That means after analyzing lot of data. Okay. So for example, image recognition in a self-driving car, where the network learns to identify pedestrians, other vehicles, and traffic signals from the camera input. It also accordingly it will apply brake, it will accelerate, or it can slow down, it can apply brake, and so on. All these things it can do by its learning process, by its own learning process. For that we have to do some help, like your quantum mechanical learning. The quantum machine learning is a special field that is part of the quantum computer. So in that it can handle huge amounts of data and with a high speed for the processing. So therefore, if you put quantum computer in the AI, it can do a lot of things. So tomorrow, actually our human life is going to change a lot by using this type of things. Okay, now types of qubit technologies, because qubit is the basic thing where we have to start our quantum computing or quantum technologies, right? So we circuits using Josephson junctions operate at extremely low temperatures, that is near absolute zero, that is milli-Kelvin and so on, and used by IBM, Google, Rigetti, like that. And pros are the fast gate operations, scalable fabrication. We have to increase this fabrication, that is 25 cubic to maybe a million cubics. So it is possible with this. Cones are sensitive to this way. This is a qubit technology, and it needs a very low temperatures, that is milli-Kelvin temperatures. Okay, how it is actually the information we are giving, we are encoding in these qubits. Energy, EF, and the charging energy, EC, so they will interact each other and they generate the oscillating energy. In that, the energy levels are very discrete. Okay, that way you can generate the quantum bit in that way. And trapped ion qubits. You see, ion, it will give actually the electronuclear spins are there, that can be spin up and spin down, that can be used as a quantum bit. Okay, 1 and 0, these are spin up and spin down. So here why it should be a trapped one? It can be done, an ion can be trapped with electromagnetic radiation, maybe with laser also. Why it is needed? Why trapping is needed? It is because of the fact that the ions, they won't stay stably. They will move with high velocities in the space, the isolated atoms. So that you have to arrest, because Doppler effect will come. So your frequencies will be changed. So therefore you have to trap that ions or atoms, isolated ones, not in a solid material, not in a crystal, like that. You have to trap, and their energy levels can be used as a perfect qubits. Okay. Then quantum dot technology. Here you have actually you can make a very nano films on a substrate crystal, and there is a lattice mismatch, that is the lattice parameter of the film and the substrate may be slightly different, because material to material these things will be different. So because of that there will be a strain, and due to that strain, to release, while releasing that strain, your quantum dots, nano dots, zero dimensional dots, they will form by the process of self assembly. So in these small dots, nano dots, your electron and hole are trapped, and the trapped electron will give this spin up and spin down, that can be used as a quantum state. So like that it can be used this way. It is a room temperature technology, and also it doesn't, okay, it is it can be fit into the integrated into the present semiconductor technology. So that is there are two additional advantages for this. Okay. So next is your photonic qubits. Photon, even laser contains a photon, that coherent photons you have. So that also can be used, but only thing is here 2 qubit gates difficult actually, but with the help of nonlinear optical crystals, which are grown here also, being grown even still, you can have this 2 qubit gates. In that actually your down conversion mechanism with the same frequency, maybe higher frequency, you can get exactly 2 photons of the half of its frequency. So those two can serve as a pair of a qubit, that is 0 ket and 1 ket. So like that you can use this technology also. And the another one is defect based qubits. Actually in a diamond crystal they are actual nitrogen vacancies, generally they happen by nature also. So these vacancies, they trap some electrons. This electron is a trapped one, so it can give a electron spin up and spin down very in a stable position. So that is also can be a very good qubit, that also can be used. And topological qubits, these are based on the exotic quasi particles like Majorana fermions, so they can also be used because they are identical to their own antiparticles, that can also be used. But of course it is potentially robust, error resistance, but not yet practically realized. It is still limited to the experimental laboratories. And nuclear magnetic resonance qubits, the molecules can give this nuclear spins in molecules, that can be controlled by the magnetic fields. So that is also another technology. Yeah, okay. So nowadays actually these technologies are complementary to each other, but they are not competitive. Every technology is having its pros and cons. Okay. And but at present actually this superconducting and trapped ions dominate the current platforms, while photonic and topological qubits may shape the future of scalable, fault-tolerant quantum computing. But I don't agree actually for this. Actually, this quantum dot technology is going to come. Maybe it may take some more time, because I worked on this type of quantum bits. It is no longer a big technology with the molecular beam epitaxy, etc. We can make a very perfect quantum dots, and with which there are two very important things. It can be integrated to the present microchip chip technology, and it can be operated at the room temperature. So therefore, this in my perspective, this is going to come in future. Okay, and then our size will be laptop. Simple this way. Okay, so that way I have okay, quantum qubits and their logic gates. You see the classical bits 1, 0 like that, and I have already spoken. So actually this the every gate it can be defined in a matrix form. Here the gate is represented by unitary function or a operation. Suppose if it is operated on a psi, then u psi becomes the this phi ket. So there are many varieties of this. Okay, these qubits can be represented in a block sphere. Any point that represents a vector that is which is joining to the center, and you can calculate this psi by using this polar and the azimuthal coordinates. Psi is nothing but the combination of these two, the alpha and beta. The probability amplitudes are given. So anything can be defined in this black sphere on this, because the probability is always 1. So its radius is only 1. So all qubits will lie on this. Okay. Of course, I cannot go much into the details of these gates. These are some variety of gates, rotations, the change of the state, and sign changing, and so on. There are controlled bits. For example, this is a controlled bit. If it is 1, then only it will go ahead. So like that you can have a swap gate, Hadamard gate. This is highly entangled to each other. So to get actually 0 ket becomes 0 ket plus 1 ket by square root of 2. So that means there is an entanglement between these two. So with that, the speed will enhance like anything, and computations will be enhanced by this way also. Computation, 3 parameters are there. One is superposition, entanglement, and interference. In these 3 ways, you can have a exponential speed in the quantum computer. That is the speciality of this thing. So like that we have variety of gates, phase shift gates, and so many other gates, control NOT gates, that is 2-bit gate. If this first one is 1, then only it will change the next one. The 0 becomes 1, and here 1 becomes 0. It flips, but the control bit should be always 1. Then only it will do that. Okay. So these are the Bell states which are having the maximally this entangled qubits it will give. So which are very necessary in using the circuits, and circuits we are going to use in the algorithm to solve any problem. Okay, so this is a 3-qubit system. In this first two are control gates, and the last one is the target one. And the first two, when first two are ones, then only the target will qubit will change from 0 to 1 or 1 to 0. Like that, I have to go quickly only. So deuce gate, this is another, it can give a rotation, a controlled rotation, as governed by this two control gates, two control bits, sorry. And C0 gate and so many other things, they are having some properties and all those things. And these are the serial circuitry. In the circuits, we have to use this serial way. We can connect in a serial way like this. If it is YX, it has to apply in a XY way. And this is a parallel gates. This can be by this tensor product. We have to calculate in that way. This is just like your jar gate in the classical digital electronics. And Hadamard gate transforms into, suppose H2 also we can do in this tensor notation only, like that you can. And this is more details about these things. And okay, now I will show you some. Okay, this is the architecture of a quantum computing platform. You see here there are a variety of things are there. In a superconducting technology, this has been made. So it needs a dilution refrigeration, and you see here are the qubits, and millikelvin to room temperature gradually it should go. It is a layered structure, 5 layers are there. For that refrigeration unit is there, and error correction circuit is there, and control electronics that will generate the microwave pulses and to manipulate the qubits. And there is a data center in which your instructions will be there. Computations also takes place before going to the quantum computer, and after the measurement has been done, it will come to here, and here this microwave pulses, and you can have a classical data. That means it will send the instructions from a classical computer to operate the quantum processor, how to work like that, and also algorithms etc. will be operated by this. So like that it will work, the whole quantum computer. It has a many varieties of things. Actually it is a hybrid type. Some part is a quantum main part, and from outside, before the instructions are going to the quantum computer, we will do those things classically, and the measurement from the quantum computer has come. It is in the form of a probabilities. So therefore you have to use the classical computing. So those things will be done by this data center. So all these things like that. Okay, so the stability, scalability, and the hardware also need heterogeneous, because we have different qubit types and different qubit technologies. All they need different accessories. So the technology is not a simple one. It is a very complicated one. So all these things we have to ensure that thing. And these are why it is a layered structure. Flexibility. It allows the layer-wise independent evolution of hardware and software, and fault tolerance, that is ensures the reliable computation despite of noisy qubits. Suppose for evolution, such type of layered structure is there. Suppose hardware is increased, our technology, then you disturb this layer only. You enhance the hardware in this layer. For it won't be, when it is in a layered form, it won't affect the noise for the other layers. And scalability also, it gives a roadmap. You can go on expand if it is in the layered form. Are you following anything? Huh? So you can interrupt me also. You can ask a simple questions in between also. Okay, at the end you will ask, because actually speaking, this needs, everything is new for us, isn't it? Because for the classical computer, we have been learning right from the 10th class, but suddenly we are going to learn all these things. Except the quantum mechanical principles, everything is new. So therefore you may have lot of doubts, and definitely it needs a lot of time to understand fully. But today it is only an introductory part. That means what are the things inside, how to go ahead, what are the basic things. If that much you understand, I am happy. I don't expect that you will be knowing everything. It is just an introductory thing. One should not think in a wrong direction. So this is the direction you should think, you should study in this direction. So that is what I wanted to convey through my this introductory lecture. Okay. So now this may be a bit interesting. Actually, overview of quantum computation, communication, and sensing. So here actually these are the three pillars of the quantum technology. I will tell some of the applications with some examples. May not be very okay. For example, drug discovery and healthcare. Actually, the quantum computer can be used to know the interactions, molecular interaction at the atomic level. That means even if you know the structure, you can know it will do like this, and the end result is this one. Or if you want a particular drug with some characteristics, you can design in that way, which for which those characters will come. This is possible only with the quantum computing, because it can know the interactions at the atomic level. So that is, which is very great actually. So then cyber security. We have this quantum computing has the capability of having the protocols like quantum key distribution, teleportation, etc. Because of such capabilities, you can have this cyber security. And we have algorithms like Shor's algorithm, etc. And financial modeling. You see, in the market finance, it is a huge data is needed. So such data also it can handle, and it can tell in which way you can invest money without any risk. So for banking and other investment firms, this is very good. And logistics and supply chain optimization. So you see this routing and scheduling problems. You see, for example, in the sky, aeroplanes are moving. There are so many nowadays. So unless until you have to have a routing, proper routing, in which second which flight is coming, which is coming closer. So all these routes has to be checked, and it should be properly guided. It is a complication network. It is not simple. So such things can be done very easily with this type of things. And energy and battery development. You see, for to develop anything, maybe a solar cell or a battery, it needs a economic way of choosing the material. But efficiency should be there, and it should be economical. To do all these things, you need a lot of simulations. So for that you need, this can be used. And similarly, climate modeling to alert the environmental disturbances like cyclones, etc. You have to do a lot of modeling, and maybe sometimes the last 100 years data you have to feed to the computer, which is not possible. That for the classical computer it cannot handle, but this can handle. So any amount of data, and process it by neural networks, artificial neural networks, and they have a decision nodes also, like a tree, selection tree, like that. So those things can be done. And challenges, of course there are some challenges. Scaling up reliable bits, that is one challenge, and control the environments, like maintaining the zero temperatures, that is also a challenge. And this artificial intelligence can be enhanced their power by using the quantum machine learning process. So because quantum machine can accept lot of huge data and processing capability also, which is needed for the machine learning. So that can be done. There are some circuits, and of course I don't have time, so therefore those things will be with that we can do. And quantum communication, that is also an emerging technology wherein quantum particles like photons transmit information in a ultra secure, unhacked way by using this quantum key distribution, teleportation, etc. Some techniques are there, and some algorithms are there. And of course, and by this no cloning theorem, you cannot, nobody can copy your information which is being transmitted from the sender to the legitimate receiver. Okay. Then applications. Okay, not only that, we have a future goals including a quantum internet. So that is also possible. But for that we need some quantum repeaters, and satellite based technology are to be needed, which is going on actually. And this already, this QNet initiative has been done in Berlin, and in a project, pilot projects have been started. China also spending a lot of money for this safe communication. So that may be perhaps it leads the world in near future. Okay. Next, this is a protocol QKD, that is quantum key distribution mechanism. Of course I cannot go into details, but this will give this will transmit the information very safely with some protocols, and nobody can copy it or nobody can disturb it. Okay. If at all there is some disturbance, it will be known to both the receiver and sender, that is actual legitimate users, and they can destroy the key immediately. So like that you have that type of things. And teleportation, that is another great thing. So this also, with this also, in no time you can send it by this with the help of the entanglement process. Of course they have to share qubits that should go to the classical channel, but this can go to the quantum channel very safely. So after getting those qubits, that also go with the speed of light. So like that you can have a safe and unhacked transmission process with this type of circuits, quantum circuits and quantum gates, like that. Okay. This is actually this is the description of various components, but I don't have time. Okay, maybe at some there is a subfield of this quantum cryptography. Again, QKD is there in that one also. It is a safe data preservation, protects against store now and decrypt later. So you can, we are using large files to store the data. No need now. So you can use this, and they are very safe. Everything has its own key. If you want to use it, open the key, decrypt it and use it. maybe after 100 years you can safely do it. It won't erase or it won't have anything, any problem for that. Okay, so like that you can have. Then quantum sensing, this is also one of the very interesting or very useful topic, and it is a high precision measurement technology that uses quantum systems like atoms, photons or electrons, and to detect extremely small changes. They like magnetic fields, gravitational field, time, temperature and so on. And it is using the quantum principles and also like a superposition, entanglement and atomic energy states, and offer unprecedented precision for navigation, medical diagnosis and geological resource exploration and so on. It can be used for very highly precise measurements. That is the quantum sensing. I will give you a few examples of this. A GPS, suppose some places like satellite dependent systems navigation is there. Actually these in the solar storms and sometimes jamming, one can jam your network here, the Wi-Fi. So such problems can be avoided by using the GPS denied navigation. There are methods that is based on the quantum technology. Dead reckoning, that is a technology in GPS denied environments like underwater, space, mining, etc. And interstitial sensing, that is another atom interferometry. Atom interferometry means it is you are using the quantum things, atom, electron and photon, these are the quantum things, and they will not change their state. It is a immutable quantities. So they will not change with the pressure or temperature or anything. So therefore that for example, it is highly sensing magnetic fingerprinting like that, 50 times better accuracy than conventional backups like that you can do. And for example here you can, magnetic field can be measured in the 50 million times less, that means high precision, 50 million times high precision than that of a classical magnetometers. So like that you can do, and already it is in the operational stage. Now they are no longer limited to the practical laboratories. So these are actually, if Boeing completed a 4-hour test flight in 2024 using only quantum guidance, and maritime, the UK Royal Navy and Australian Navy conducted successfully long duration trials in 24-25. And defense, UK Ministry of Defense and US DARPA have invested hundreds of millions into quantum issued drones and missiles. In the defense sector also you can have a lot of advantages, and no classical things can compete with that. You have to switch from the classical to the quantum. So essential for our security. And medical imaging breakthroughs. Actually now these medical diagnostics, they are shifting from the macro to molecular. That means tumor level to individual molecule. Suppose a single cancer molecule is there, just it is born or modified with the mutation, then you can't really identify that at its molecular level. Unless until it becomes a tumor, you can't identify. So therefore, with this type of advanced quantum technologies, you can identify at the very beginning, and you can safeguard from such deadly diseases. Okay, so like that you can have. And already some magnetocardiography machines have come that map the magnetic field from brain or heart. These magnetic fields are very, very minute, but still these quantum based devices can identify, can measure, and you can avoid such diseases in the very beginning, okay. So then portable brain scanning. Actually nowadays, instead of this huge big MRI machines, something like a helmet type of thing have been developed with the quantum technology, and while moving the patient, the activities will be different, isn't it? So that also can be recorded, which are needed sometimes, and by keeping a helmet size type of MRIs. And quantum neurosurgery, that is actually now a single photon detector have been invented, and it can be coupled to the medical microscopes, and you can see molecule by molecule. So that type of great advantages are there with this. And the quantum MRIs already told, and resource exploration. You see, geological resources like mining, oil, and tunnels, caves, so many things you can detect very easily with high precision. That is very important. Okay. So like that, okay, I will tell you at least this last this thing to make you understand what is the advantage of this thing. Okay, this is called a interferometry algorithm, the Ramsey interferometry. It measures the phase difference accumulated by a quantum system over time, used to detect extremely small changes in frequency, magnetic fields or time intervals, and it can use the foundation of, it is a foundation of atomic clock and high precision sensors. How it works? Actually, initialization start with a qubit 0 ket, and then you apply a Hadamard gate, so that will give a plus ket from 0 to superposition of two kets, 0 ket and 1 ket. Superposition has come here, and then apply this phase. So what does it mean actually? It works as a beam splitter. You see, in the normal interferometer, you have a light and there is a beam splitter. One part will go to the fixed mirror and another go to the other moving mirror. So it will, by moving this in a particular time interval over a length, it will give a path difference that is converted into the phase difference, and it will you will have a interference pattern here. And similarly, you can have a beam splitter here, and for an interferometer, and phase accumulation over a period of time, it will, this one will measure the phase shift in a particular interval. What does it mean? Magnetic field is there. If you are moving from one place to another place, it will change slightly, very marginally, very small amount. So that phase difference it will measure. Okay. So over a time t. So this introduces a phase shift phi proportional to the field being measured, then represented as a Z rotation gate. This is done by a Z rotation. This measurement will take place by this Z rotation gate. Then apply this Hadamard gate. Actually, if you apply 2 times Hadamard gate, it will come, you will get the actual measurement. That means you will get a phi measurement. Suppose if the phi is 0, then the measurement, that means magnetic field while moving from this place to this place is not changed. There may be a small change. So that can be measured, that can be estimated with quantum enhanced precision. So with that you can measure the variation. small, minute variations. Actually, this is 50 times, 50 million times precision than the classical bit. So therefore, actually magnetic field of the earth is a constant. You can't really you can't really measure its changes from in a kilometer or a 4 kilometers. So but still here, because there will be a small changes, because there is iron mining, mines may be there, some amounts may be there. All these things can be predicted by this thing. And sometimes for the GPS, they will act as a landmarks. Oh yes, there is a small change in the magnetic field. I started from that place. So how much distance from that place I have gone? Like that, it will give a this GPS type of navigation system. So, and it will take the mines, information about the mines, fishing, what not, oil, everything it will tell with a high precision. That is most important thing here. So that way you can do a lot of things with this measurement. Here actually it is very similar to that your classical interferometer. Okay, so like that. Okay, there are some techniques for quantum algorithms to solve, that means a methodology, a plan of equations that will do some computation to get a final result after computation. So for that some techniques are there. Those techniques are this thing, that amplitude amplification, quantum Fourier transform, quantum phase kickback, quantum phase estimation, quantum walks, and so many other algorithms also there. And then by using that, you can develop so many algorithms for different purposes. So these are the various algorithms which are available with this computation, with this quantum technology, and each are having some advantage. For example, Shor's algorithm efficiently factors large integers for breaking classical cryptography, and so on. For various applications, we have various quantum algorithms which gives a high precision measurement and with a high speed, exponential speed compared to the counterpart classical computer. Okay. Next is I think this is last one. Okay. So some of the transformative benefits by combining quantum computing with AI, the drug discovery, as I told you, because of the, we can simulate the molecular interaction and then you can discover new medicines. Financial modeling, because of its huge capacity of handling lot of data, it can enhance the power of AI. And logistic optimization, using this quantum powered AI, logistic companies have explored traffic flow optimization. This helps in reducing congestion and improving the efficiency. Then quantum machine learning, this emerging field focus on creating quantum versions of classical algorithms like a neural networks with decision nodes and clustering techniques also there. And to have a reasonable scaling, these hybrid systems can be used. That means some part will be done by the classical processor and the main part, maybe crucial part, will be done by the quantum processor, and it serves as a unique computer and for all practical purposes with limited qubits also we can do a great work with this type of things. And okay, so there are a lot of opportunities with these things I have seen one advertisement on 21st January, and 2.18 crore annual package is there. If you know QC, AI, ML and DL, and you should show your capability to help this discovery team, and you can, that means a lot of jobs are available for you even right now, though the computer, quantum computer is not coming to the commercial scale, but still they are in the factories or manufacturing units and some laboratories and some government offices also. These are there, and they need some experts in these fields. I wish all of you study right from now, and then you will become an expert, and by the time you take your degree you will go with some certification or some minor degree, whatever it is possible with your institute, and then you can get a very good jobs. Okay, so this is, thanks for your kind attention. Wish you all the best for a bright future with research and development base. Now a few questions you can ask, still we have some time. Okay. So questions, I wish to answer some of the question, particularly the students. Who will ask the first question? Ask something. You see, no question is meaningless. My answer may be meaningless. So you please ask me anything. Okay, maybe about your future with respect to the quantum computer, or any other questions related to this quantum computer, or maybe in some other physics also. Please, I will be happy only when I listen some of the questions from you. Who will ask first, the boys or girls? Evaro? I think girls' strength is much better than boys' strength. So who will ask first? I think girls should take the first advantage of this. Please ask some question. అడగండి, తెలుగులో అడగండి. ఓకే, గుడ్ గుడ్. సో యాక్చువల్లీ మైక్ ఏదైనా ఉందా, స్పేర్ మైక్? అమ్మాయికి ఇవ్వండి.